Now in operating system, we'll see about the memory management, very important topic. What are the memory management strategies? The objective today is we'll talk about the memory and memory hardware, then various MMT, that is memory management techniques, which will include paging and segmentation, and also we'll see some examples. So the basic idea or the basic goal always for any memory management strategy is that we want to allow multi-programming, that we want the processes to be in memory and as many as processes to be in memory. But one more thing is there is memory and the size is limited. So how to get the process, all the processes inside so that the execution is fast, we'll see about all these strategies. For any program to be executed, it must be mapped to absolute address and loaded into the memory. We'll talk about these addresses, don't worry about that. All these addresses I'm going to tell you. But the basic idea is that for any program or any instruction or any data, if you make a program, say you make a program of Fibonacci series or factorial, then the instruction and data, all these program generate some error, and the program generates certain address. The address is what? These are the absolute address. But when the program terminates, the memory space is being freed, or you can say the program terminates and its memory space is declared available so that next program can be loaded. And in order to improve the CPU utilization, we want several programs to be kept in memory. And this memory management scheme is closely related with the hardware design also. So what are the management or memory management activities for which operating system is responsible? First of all, to keep track of which part of memory are currently being used and by whom. Whenever I am talking about memory, I am talking about the main memory, okay? So deciding which to be loaded, when the space is available, and then allocating and deallocating memory space as required. So basic hardware is something like this. Just take, whenever I am speaking, just have a look on this diagram also. That means the program needs to be bought. If this is your backing store, you can say hard drive, backing store. Now the program has to be bought into the memory. So this is the memory from the disk. If this program is in this memory, main memory, then only it can be executed. So the main memory and register, they are only stored, they only the places where the CPU can talk. So CPU can directly deal with two things, main memory and registers. So register access is generally one CPU clock, while the main memory access can take various cycles. And in between this main memory and CPU register, you will find the cache also, cache sitting in between them. So we have some protection strategy also, that is a pair of base and limit register. These are all hardware stuff. So we have base and limit register, which defines the logical or virtual address space. Please understand, we'll be talking about logical and actual, that is the actual this space. So this logical or virtual address space, the pair of base and limit register define this. For example, see, this is what? This is your base, this is your limit, right? How you have gone to this limit, or how we have received this limit? What we have done is, this is the upper limit. We have subtracted these two, that is the lower and upper, or you can say you have subtracted, or this space between the base and the highest one for any process is the logical address space. I hope you got the idea. This is the logical address space for this process. Now there are address binding. We'll talk about various address binding. First of all, address binding means whenever you have a program, there are instruction data and they bind themselves to certain memory address or memory part. So the collection of processes on the disk that are waiting to be bought into memory for execution, they are kept in the input queue. So processes, they normally reside, or they can reside in any part of the memory. If this is the main memory, it can reside in any part. So addresses in the source program, they are generally symbolic. What I mean when we say that the address in your source program, like the factorial or the Fibonacci series program, you say the addresses in the source program, they are generally symbolic. Why? Because the compiler binds these. Compiler is what? Compiler is a program which converts your program or your basic program into the code which is understood by the computer. That is the machine code. So compiler does what? Compiler has various aspects, we'll see about that. So compiler binds these symbolic address, which are the addresses of the source program, to the relocatable address. And what are this relocatable address? I'll show you just now. The linkage, after this we have linkage and loader. This binds this relocatable addresses to the absolute address. Before going to that, let us see first of all what is the address binding. First of all, address binding of your program's instruction and data to certain memory addresses can happen in 3 different stages. Means these are the stages. First of all, you have compile time, then you have load time, and you have execution time. So what I'm trying to say is, whenever you are dealing with or you are talking about address binding of your program instruction data, this can happen at 3 different stages. First is compile time. That is, if the memory location is known previously, absolute code can be generated. But if you recompile, it has to start from the initial. The recompilation has to be done if the starting location changes. How about load time? Here, it must generate relocatable code if the memory location is not known at compile time. You will be understanding this with the diagram. Execution time is the binding is now delayed until runtime. If the process can be the process can be moved easily from one part of the memory segment to another part. This you can do. So it needs some certain hardware support. That is, you ought to have some base and limit registers. So these are the steps which I was talking about. You have a source program. As I just said, you can have any source program. Now the compiler and assembler does what? It will give you an object module. So this place where this binding is there, this is called compile time binding. Now when the object module is there, there can be other object modules which linkage editor can link, and then it will give it to the load module. And then load module can take some other like system libraries like stdio.h or conio.h. All these will be combined, and this loader will take all these. And this is the load time binding. So this is the binding going on. And then after that, the actual exe or the binary memory image will be made. This is the dynamic. You can have some dynamic linking. At this time, the binding is execution time or runtime binding. So what is the difference between a logical versus physical address space? So what is logical and physical address space? Please understand it very carefully. You have a CPU and you have a memory. So what CPU generates or what CPU use is the logical address, which is the address which is not actually the memory address. But the memory or the memory unit sees some address, and what is that address? It is the physical address, which is actually going to be placed in the memory address register for actual addressing. These are the actual address. So the compile time and load time address binding methods, they generate identical logical and physical both, which is generated by CPU and generated by the physical address. So the execution time address binding scheme result in differ. The result is differ. That means different logical and physical address. So the logical address space, these are set of all logical address generated by a program, or you can say generated or seen by CPU. While the physical address space is actually, these are the set of physical addresses, actually physical addresses which are corresponding to these logical address. So all logical address will have a corresponding physical address. Who is going to correspond? Who is going to bind them? The memory management unit does that. So this is a hardware device that does the runtime mapping from your virtual or logical address to the physical address, because physical address is the actual address. What this MMU does, this is a memory management unit. So hardware device that maps virtual to physical address is the memory management unit. So what it has, I'll show you with the diagram. This MMU scheme is simply the value of the relocation, that is the base register, is added to every address generated by the user process. So see, if a logical address of a user process is 346, so you have a relocation register, that is the base address register. This is added, so 14000 will be added with 346, and now this 14346 will be the actual physical address, and this will be actually be in the memory. I hope you got the idea. The user program only deals with the logical address, and it will never see this address, this kind of address. It will never see this address, right? Now dynamic loading. What is dynamic loading? See, if this is a disk, and this is your main memory. Now, whenever it is required, a routine, a function, a procedure can be bought. It can be bought into the memory. So the dynamic loading is simply the routine functions procedure is not loaded in the main memory until it is called. All routines are kept in the disk in the relocatable load format. The main program, only the main program, only the key program, only the key part is loaded into the memory and it is executed. And whenever the routines or functions are being called, it will first check whether it is there or not. First, if some routine is called, first it is going to check whether it is in the memory or not. If it is not in the memory, then it will be called from the you can say backing store. Okay. So the control is now passed to the loaded routine. This is the dynamic loading. So what is the advantage of dynamic loading? With the routine which are being unused or which will not be used, why to load it? And one more thing, dynamic loading doesn't require operating system support, right? It only gives you the library routines. In order to implement dynamic loading as a programmer, it will give you library routines, but dynamic loading doesn't require special support from the operating system. Dynamic linking and shared libraries. Now we have dynamic linking also. First of all, just understand static linking and dynamic linking. So we have various libraries. Your function is just your function or your program is just not the code you have written. It is combination of the codes which is given by the programming language. The system libraries. System may have some libraries you may be interacting with. So the system language libraries, these are treated just like any other object module, and they are just combined by the loader into the binary program image. Means your program along with the system language libraries, both are seen as an object module. They are combined. This is static linking, simply static linking. But what about the dynamic linking? In dynamic linking, the linking is not done as of now. It will be postponed until the execution time. It will be done only at execution time. So you ought to have some stub, means there has to be some address. Code is nothing but, this stub is nothing but a code that indicate how to locate the memory resident library routine, because eventually we are going to get the routine. So some address has to be there. That address is kept somewhere so that the program knows when the things are going on. Okay, this is the address. When I will execute it, I will go to this address. So this stub will replace itself with the address of the routine and will execute the routine. And next time the code segment is reached, the library routine is executed directly with no cost for the dynamic linking. In this scheme of this dynamic linking and shared library, all processes that use language library will execute only one copy of library code. This is very important. But unlike this dynamic loading, dynamic linking does require the support of operating system. So if the process in memory are protected from one another, how to know that we have some routine already present? So the operating system is the only entity that can check or to see whether the needed routine is in the another process memory space or not, right? Then we have shared library also. We have library which can have different version. So library can may be replaced by new version, and all the program that will reference these library will automatically use the new one. This is about the shared library. So the version information is included in both the program and library so that the program won't accidentally execute any incompatible versions. Then we have swapping. See, I'll show you the diagram first. This is swapping. Simple swapping is, this is your main memory. Some place is taken by operating system. Another place is used by the user space. This is your space. Now swapping in, swapping out is simply you take out some process which are idle, that can be taken out, low priority process, and this process, high priority process, you want this to be executed, so it is brought into the main memory. So taking out, taking in, this is the swapping in, swapping out. So swapping, this is nothing but a process can be swapped temporarily out of memory to the backing store, and then it can be brought back into the memory for continued execution. This is simply the roll in and roll out. And the higher priority process, when it comes, the lower priority process is swapped out. It is taken out, and the place for higher priority process is being made. And it involves a certain transfer time, because you are actually transferring. When you are transferring, you are not doing any good work. So swapping requires a backing store, the place where you can put like the hard disk or the tape drives, etc. And the system actually has a ready queue where all the process are there which are ready to be run. So CPU scheduler now calls the dispatcher, before running a process. Now dispatcher does what? It will check if the next process in queue is in memory. If it is not, there is no free memory region. The dispatcher will eventually swap out a current process which is simply idle and swap the desired one. Then after that it has to do some housekeeping, that is, it will reload the register and transfer control to the process. And the context time is also there because we are swapping. So we just do or swap those which are completely idle, and this is what is being done. Then we have contiguous memory. Contiguous memory is simply like this. See, if you have an area, if this is the space, this is the contiguous memory, and these are non-contiguous memory. So in line is the contiguous memory. So memory are usually divided into two partitions, one for the OS, one for this is OS, this is for user process. So OS is usually in low, since we have interrupt vectors there. So contiguous memory location, here each process is contained in a single contiguous section of a memory. Now memory mapping and protection is very important because the operating system needs, because we have operating system here, we have user process here. So the operating system must be protected from the user. These two have to be protected. So from the user process, and user process must be protected from one another. So here we use a relocation register with a limit register for protection. What is this relocation register? It contains the smallest physical address, and the limit register which contains all the range of the logical address. What MMU does here, memory management unit, it maps the logical address dynamically, adding the value of the relocation register, which is simply the addition value, same for all. So this mapped address is sent to the memory now. So when the CPU scheduler selects a process for execution, any process, the dispatcher will load the relocation and the limit register, right? And since every address generated by CPUs checks against these registers, we can protect both the operating system and the programs from one another, or data from one another, from being modified accidentally by this running process. So this is what is done. The CPU generates some address, the base is added. Now if this CPU is greater than or equal to this base plus CPU address, if it is greater, then we go ahead, otherwise we trap an error. Then we add the limit also, and if it is less than this whole is less than the value which is coming, then we go to error, otherwise we address it to the memory. So the relocation register scheme provides very efficient way to allow operating system size to change dynamically. So there are transient operating system code also, that is operating system code that comes and goes as needed to save the memory space and overhead for unnecessary swapping. And then we have memory allocation. There is a very simple method, first of all, and this method is no longer used, right? So first is we just divide the memory into fixed partitions. Each partition will contain one process, and the degree of multiprogramming is only dependent on the number of partitions. So when the partition is free, the process will be selected and from the input queue and is loaded into the free partition. And when the process terminates, it will free the space, and this is not being used. There is another process. Now we have a table. There is a table. The operating system keeps a table indicating which part of the memory are available and which are occupied. There is another method, as we just said. Initially, all memory is like a whole. It's all free. It is considered like a very, very large block of available memory. And when the process arrives, we search for a whole large enough. And if we actually find one, we allocate only as much memory as needed. So when the process enters the system, they are put into the input queue. And when a process is allocated space, it is loaded into memory and then can compete for or can go for CPU. And when the process terminates, it will release its memory. So we have a list of available block sizes and input queue, and the operating system can even use the scheduling algorithm in the input queue. So memory is now allocated to process finally. So there isn't a hole now large enough to hold the next process. So operating system can then wait until a large enough block is available, and it can skip down the input queue to see whether the smaller memory requirement of some other process can be met. So what happens in general, a set of whole of various size is scattered, here at any point of time. So when a process arrives and needs memory, the system searches this set of whole that is large enough for this process. And if the whole is very large, it will split up So one part is allocated to the process, other will be returned to the part of the holes. So once the process is terminated, the memory block returns to the hole set, and the adjacent hole are merged to form one larger hole. So what are the solution to this dynamic storage allocation problem? We have first fit, best fit, worst fit. This is better and faster because we allocate the first hole that is big enough. In best fit, we allocate the smallest hole that is big enough. Worst fit, this is not as good as other two because it allocates the largest hole. And these algorithms, they suffer from external fragmentation. We'll talk about the external and internal fragmentation in the next discussion. So till then, thank you so much. Take care of yourself.